Welcome to Solutions to Homework Set number 7 for ECE 376. In this homework set, we're going to be using a student t-distribution to analyze data that we collect in lab. So starting out, to collect the data. So here's the data. What I have is a capacitor going to my board. I'll connect it to 5 volts. It then discharges through ground through the 100K resistor on your board. On hyperterminal, I can see the voltages, so they're charging to 5 volts. Disconnect the wire, let it discharge. That's the voltage versus time. If I copy that data to the clipboard, I can then import that into MATLAB. Now MATLAB, what I can do then is do V equals square bracket paste. That'll paste the data that I just collected into MATLAB, and I can plot it. If you plot the data, that's what it looks like. This last part over here is the data that I want. So I'm going to truncate it between, say, 300 and 500 data points to get my capacitors at discharges. The net result, after doing that 3 times, is I have 3 sets of data. This is a 100 microfarad capacitor discharging, measured with your PIC processor. Now I want to convert that to a number, and the number that I want is the capacitance. Well, this is the code that I used. It just, well, the heart of it is the main routine. Turn on the serial port, read the analog input, convert to voltage, ship out the data, and repeat. This loop should take 100 milliseconds. It actually is a little bit off because the serial port takes a little bit of time. I'm sending 7 bytes, you have 5 bytes of data, plus a decimal point, plus character return line feed. That's 8 bytes. So this loop right here is actually right around 108 milliseconds. That's my sampling rate. Once I have that data, I can sit there and determine what is my curve fit. What I want to know is that time constant. That is actually A e to the minus t over RC. I want to find C, so I want to find that constant. The trick is take the log of both sides. If I plot log of V versus time, I'll get a straight line. The slope is that guy. That's minus 1 over RC. So take my data. Here's my sampling rate. Again, the sampling rate is a little bit wrong. It should be about 108 milliseconds. Because of this, my answers will be off by about 8%. But anyway, there's my data. My basis is time and 1, because I want to have it in this form. Basically, BT plus C. There's my basis. Do a least squares curve fit. I'm going to curve fit the log of the voltage, because that's what's linear in time. And I get 2 numbers. This is the second number times the second basis element, 1. So that's log of A, which I don't care about. This is the slope. That's what I do care about. That's minus BT. So that's the first data set. My constant B is minus 0.1093. Second data set, third data set. And just for fun, let's plot it. I'm going to plot T versus log of voltage. Should be a straight line in blue. T versus my curve fit in red. And you can see the data pretty much is the straight line. And what I did is I found the least squares curve fit for the data that uses all the data, not just 2 points to determine a line, all the data, and that helps filter out the noise. Now, I want to calculate the capacitance. So here's my data. My resistance is 100K, and C will just be minus 1 over R times B. And it gives you 91.5 microfarads, 91.0, 91.1. It should be 100 microfarads, because that's the capacitor I used. It's off by about 8%, just because my sampling rate is actually 100 milliseconds plus the time it takes to send the serial data. So that's one of the reasons the data is off by a little bit. But that's what I measured. Now that I have 3 numbers, I can do a t-test. With 3 data points, I can find the mean. I can find the standard deviation from a t-table. A t-table, I have sample size of 3, meaning 2 degrees of freedom. So I come over here at 2 degrees of freedom. If I want 5% tails, I go over right here. I want to go left and right 2.92 standard deviations. So doing that, going left and right 2.92 standard deviations from the mean, tells me that I'm 90% certain that the next reading I get is going to be somewhere between 90.5 and 91.9 microfarads. If I want to know what is the true reading of this capacitor, that's a population question. There is an average. I don't know what it is, but I can estimate it. The average, or the population, drops as the square root of the sample size. So take the standard deviation that I calculate, divide by the square root of 3. Now go left and right 2.92 standard deviations. This says the actual value that I measure, actual measured value technically, is between 91.67 and 90.82. Again, it's not 100 microfarads because I haven't calibrated my capacitance meter. It's off a little bit because my sampling rate's off a little bit. But as it currently is, this is my confidence interval. That's part A. Part B is do something different. And what I did is I flipped the capacitor around and used the incorrect polarity. So instead of having minus going to ground, I have the plus going to ground, measure the capacitance. Repeat, here's the voltage versus time. Repeat, throw that in MATLAB, form your basis function. I'm going to curve fit log of V versus time, and I get 3 different numbers. Calculate the capacitance. Here's the capacitance with the reverse polarity. If I plot voltage versus time and get the blue curve, and what this kind of tells you is this isn't a straight line. The slope tells you the capacitance. The slope is changing. That tells me that for this electrolytic capacitor, if I use it reverse polarity, the capacitance changes with voltage. Something I didn't know. But anyway, that's what you get. I can now, like same as before, find the mean, find the standard deviation, find the confidence interval. So with that, I'm 90% certain that the next reading I take with this capacitor with the incorrect polarity will be somewhere between 81 and 85 microfarads. Finally, comparison of means. I've got these two populations. The correct polarity is right around 91 microfarads. Incorrect polarity is right around 85 microfarads. Suppose I want to know what's the chance that a capacitor will have a higher capacitance with the correct polarity than incorrect. That's a t-test. To do that, what I do is I form a new variable, W. That's the difference between the two. There's A is correct, B is incorrect. The mean of W is just the mean of A minus mean of B. The standard deviation of W is the square root of the variance. The variance is the sum. Variance is add. So now the variance, or standard deviation, is 0.66. When I do that, I have this W variable, looks like this. It has a mean at 7.61. What I want to know is how far away is 0. Because to the right of 0, A is greater than B. To the left of 0, B is greater than A. If I can find this area, I can tell you the probability that the capacitor has a higher capacitance when used correctly than incorrectly. Turns out this distance, in terms of standard deviations, is 11.51 standard deviations. That's your t-score. To convert that to a probability, again, I have a sample size of 3, meaning 2 degrees of freedom. T-score is 11.51. So I go over here at 11.51, and it's between these two numbers. Close to 0.05, it's about 0.004, eyeballing it. So it's like 99.6% certain that using the capacitor with the correct polarity will have a higher capacitance than a capacitor with the incorrect polarity. That's for an individual. If you care about populations, in that case I divide by the square root of n. So take the variance divided by n, square root, can be divided by square root of n. This is the standard deviation for the population. This is the difference between the two means for the populations. So overall, overall means population. Overall, the t-score is 19.94. So go over 19.94 standard deviations, close to here. It's almost 99.9, about 99.85% certain that the correct polarity will have a higher capacitance than the incorrect polarity. So that is homework set number 7 for ECE 376. Collecting data with your PIC processor and then doing something with it, analyzing it using a t-distribution.